Here's an old amplifier then. This is a Rogers A100 from around 1975. And Rogers weren't so well known for their amplifiers, it was more the loudspeakers that made their name. So I've got no familiarity with this thing at all. It does power up, but I know that one channel's dead, and we've also got a missing knob here and button here. But anyway, let's open this up and see what we can find. Yeah, there's a lot of metal work to come off to get inside these old amplifiers, but we're in there now. It's proper old school when you look inside here. It's not something I would normally look at. Just doesn't make sense economically to look at something like this. So I'm just doing this one for curiosity, really. So we know that one of the channels is dead, and that's already been sort of disconnected and the like. So we can take out. Yeah, it's quite tidy actually how you can take out the whole sort of power amp section like this, and you know, we'll work on that in isolation and figure out what's going on with that. I think I understand the transistors are gone, so we'll have a look at that separately. But I was curious, just, you know, this thing is nearly 50 years old, and you see in a lot of our modern amps where we you know, within a few years and you've got dry caps, and we've, as I say, nearly 50 years old. And let's just check these big reservoirs. Now look at that, it's brand new. I've been round the board, they're all kind of reading the same. So that's, you know, I kind of thought when I was going to look at this that this is something I'd have to replace everything in sight, but when you see this, it's quite amazing, something this old. Here's one on the board here, smaller capacitor, still less than half an ohm after that length of time. So, very good. Alright, so we'll just get this main unit, we'll put this main unit to the side and just have a closer look at that power amp section, see where we can take that. So here's our power amp section module, and very nice little module actually. You know, when it's made like this is very easy to work on. You know, so anyway, our main transistors are connected to this board via some wiring, and I was told that these transistors had blown, they were replaced and then they had just blown again. But when I disconnect from the main board here and we just do a basic DMM test here, that's reading okay, and both transistors were the same. So I can't really argue with that. So that's an interesting discovery. Anyway, it means I don't need to replace them. So I'm going to connect these back up, and I think what we'll do is we'll just attempt to power this board from a bench power supply, and we'll see just what happens, see what current we pull, and at least by using a bench supply we can control what's going on and just make sure nothing else goes up in smoke. So let's do that. We'll connect that back up and put some power on the board. So before I go and put power on this module then, and given it's actually just such a quite a nice tidy module to look at, a nice clean layout, I thought I would reverse engineer the thing, and that then gives me, you know, the means to simulate the thing and look at any kind of funny behaviour that we might see. So this is a schematic here, and normally I don't show schematics in full detail, but this unit is near 50 years old, and so I don't think there's any real harm in showing this here. So it's all very kind of standard stuff. We've got an op amp on the input working as our differential amplifier, and then we've got some current sources and sinks, and we've got our classic base emitter multiplier to give us our bias here. So we've got a variable resistor in here to tweak our bias, and then Interestingly, for the day, back in the day when these kind of amplifiers were done, we didn't really have matched N and P transistors, so it uses N types in both sides for the output driver, and then we've got an N type drive in the top side and a P type drive in the bottom transistor there. So this is kind of just the sort of thing you would see back in when this was developed. So this is all very standard, all very good, and so we can actually go and simulate this now. So I've got a 1 kilohertz source on there, and I think I've just got like a quarter volt coming in, and here we are, nice clean sine wave on the output. And I can look at my distortion. So if we look at the error log there, we can see that we're down about 0.039% distortion. So that's all pretty healthy. We'll maybe do a real measurement on the final unit when we get it back together and see how it compares with that. But pretty decent numbers. And then of course the other thing we can do is we can look at the frequency response. So let me just change some settings and we'll do that. Here's our frequency response plot then, and I'm running from 10 Hertz up to 1 meg, and we can see roughly about the 1 kilohertz mark we've got a 31.3 dBs of gain. So that will make sense. And if we then look for sort of 28.3 on the graph, that's going to tell us our bandwidth, and we're just roughly about 180 kilohertz of bandwidth there to the 3 dB point. So that's all nice, and a very nice graph. Everything's all stable and smooth, so quite happy with that. So we'll use that as that's our reference, and we'll see what the actual hardware does. So let's now go and power it up and see what we find. Right, so I've got the module here connected to a bench power supply, and that lets me control the current, and it lets me ramp up the voltage slowly. And with no input, the input's just floating here, but the input op amp does have a ground reference via this R2 here. So that should all be okay even without an input. It's maybe just going to be a bit noisier, but it should be stable enough. But what I find is when I look at the output of this op amp here, and let me just, I'm about 13 volts now, let me just wind up a little bit. And what we find is beyond a certain point we go very unstable here. You see it's moving around when I touch things. And if I put just when I connect the input, so just the capacitance of that input lead there makes it stable again. So there's something very kind of flaky going on there. And whether that's just what this thing does or not, I don't know. We'll compare with the other module, but that's certainly not happy. And maybe this is what the problem's been. When the previous person looked at this, they just turned it on. It was drawing huge current because it was unstable, and I suspect they just didn't have an input connected that helps with that. Right, so I've got the module function generator connected to the input, and we're looking at the output on a scope. And if I turn on my function generator, we can see we get a nice enough output. I've got 10 volts per here, and I've got a 25 volt plus and minus 25 volt power supply. So I can then turn my amplitude up, and we should see the output clipping. There it's clipping there, just I don't know, about 23 volts, something like that. So that all looks healthy. However, there is some characteristics here that are a bit concerning. If I leave it at 200 millivolts, and then we look at our frequency, and if I go up in frequency towards the sort of higher end there, up towards 20k, then we start to see some artifacts. You can see there's a little kind of unpleasant looking notch, and as we increase our frequency that just gets worse. And then if we go up sort of 100 and something kilohertz, we can see there's some oscillation going on in here. So none of that looks very nice. Whether it's related to the earlier problems, I don't know. You know, the transistor models that are in here are like 50 years old or more, and they, you know, they had their limitations at that point in time. So maybe this is just what we get. So what I'm going to do is I'll take the other module, which should be working. It's not had any repairs or anything done to it. So we'll take that and do the same measurement, see if we see the same characteristics. So I did check the other module, and I found that the instability thing we saw on the input side here, that was present on the other module also. You know, so it obviously expects the sort of the circuitry that comes before this thing to be connected up before this becomes stable, and that seems a wee bit questionable in my mind. You know, I'd really expect a module like this to be stable in its own right, but that's what they've chosen to implement, I guess. Anyway, at least we're seeing consistency between the two modules. We might take a look at seeing if there's anything sensible we can do to improve on that, but you know, we're not going to get into a whole redesign exercise here, and I suspect that any simple change will have some other compromise. You know, it might compromise on the frequency response or give us some other kind of headache. So that was the stability thing. In terms of the waveform shape, the other module performed better, and I quickly realised the reason for that. And what was happening here is that in the repair module, this is our bias adjust here, and I had set it to the minimum, and that's just a careful thing to do. You know, if transistors have been changed and you're powering up for the first time, it's always better to set your bias to a minimum and then adjust it upwards. So I had the minimum bias, and that was the problem. I've now put some nominal bias on, and our waveform's very good. If we, this is just 1K we're looking at here. If I go up to the 20K where we saw the problems before, and then we can see it's perfectly clean. There's no funny business going on there at all. And let's go all the way up. If we go up to a couple of 100 kilohertz, say, and that's still perfect. So very happy with that. And that's just a nominal bias. You know, we're not even on the proper power supplies. Nothing's sort of tweaked up. So things should be just fine when we're back in the main unit and everything's connected to the proper supplies. So I have done a frequency response measurement. Here's the frequency response here, and it's extremely close to the simulation. You can see here at 1K I've got 31.45 dBs again, and then if I go up to sort of 100K, I'm just 30.15, and the simulation's within a couple of tenths of a dB of this. Even when I go further up the graph here, it tracks very, very well. And this is a nice graph. You know, there's no funny business going on here. It's all very stable and smooth. So quite happy with that. So that's probably all I need to do with that. I think the next thing is we need to get it back into the main unit, get the proper power supplies on it, and we'll maybe repeat some of these measurements. We'll maybe do a distortion measurement, see how that looks. So I thought I would simulate the funny effect that I saw when I had the minimum bias set, and the simulation shows this quite well, and you can see the effect just up here, same location we saw in the actual measurement. And I mentioned that when we introduced some nominal bias, this disappeared, and again I can show that on the simulation. But of course, bias, we understand, is related to minimizing crossover distortion. So the crossover point when this sine wave goes through 0 volts. So we would expect to see any effects of lack of bias at this point here. So why then are we seeing it up here? How can we then say that any artifact up here is due to lack of bias? And so I thought I'd better explain this. And what's happening is that when I was measuring the module there, I did not have a loudspeaker connected. I didn't have any kind of load. So I'm kind of representing that here. I've put 8 meg as opposed to 8 ohms. So essentially there's no loudspeaker connected. And what we've got here is something we call a Zobel network, and that's just a filter at the corner at 160 kilohertz there. And this is just to give the amplifier a load at high frequencies. Your speaker is essentially an inductor, so at high frequencies it's going to go kind of high impedance, and your amplifier's not got a load, and there's questions over stability. So we put in an arrangement like this RC here, and this, because we've got the capacitor here, what we find is that the current through here is not in phase with the voltage. So if I go and look at the current through there, or through that resistor, which is going to be in phase with the voltage across it, then we see that the issue appears at the crossover point there, and that translates up here. If I then go and introduce my loudspeaker, so if I remove this 8 meg and just make it 8 ohms, what we will find when we run that simulation is that we get the crossover point where we expect to see it, because the current is flowing through this resistor here, and we get some slight artifacts through the Zobel network that line up with that crossover point. So that's the reason it appeared in what we would believe is the wrong place. It's just because our load was not purely resistive. It had this capacitor in place, which meant the voltage and current were not in phase. So there we are. Right, let me go now, and we'll connect this module into the amplifier and see how it behaves there. Alright, so we're beginning to start to put this thing back together, and so I'm connected to the main power supply here, something like 42-43 volts, and I'm using my usual damage limitation resistors at the moment. Then I'm monitoring the voltage here across the emitter resistors, where we'd normally look at our bias, and I've set my bias to minimum. And even with that, if there was any kind of short or high current going through the main transistors, we're going to see voltage across there. So that will quickly tell us something is wrong. So let's just power up now, and we're looking for not much activity. We'll see a slight rise in this voltmeter, but hopefully not much. So there we go. We've got about 2 odd millivolts there, which is fine. There's nothing much happening there. So we'll adjust our bias up now, and I think I'm going to go for something like 25 milliamps of bias, which is about 11 millivolts here. So we'll just go up a scale here. So we're reading about 2 just in the residual there. So I even had to make a tweaker for this variable resistor. It's so old that I never had a tool to do that. So, but here we go. So we'll adjust this up to about 11 millivolts. I'm starting to see it creep up there, so that's obviously all working okay. It's easy to overshoot on this, so we have to be kind of cautious as we go up. Yeah, that's fine there, and it'll move around as this thing warms up. So I'll probably just let it sit like that for a while and just check on that voltage, and probably need readjusted, and then we'll put the module back in. And obviously, this adjustment cannot be done with that module installed, so it must be kind of pre-tested and preset to that level, or some whatever. I don't know what level they've chosen, but I'm just using a kind of nominal 25 milliamps to start with here. If we look at our distortion and it's not too clever, we'll maybe revisit that. But for now, that's probably fine. So we've got our module connected to the audio analyzer now, and I'm outputting 1 watt here into 8 ohms, and the spectrum looks quite good. Second harmonic, third harmonic, they're way down,
so all looks quite reasonable. However, what I find is when I ask for a little bit more power, things go dramatically wrong. So let's do that. I'm going to tweak it up now, so we're looking at 5 watts on the output. Right, so this is us looking at just over 5 watts on the output then, and you can see our harmonic content's gone a bit crazy here. So there's something far wrong with that. We shouldn't be getting that level of distortion at that sort of power. And if I compare with the other module, we find here it's much cleaner. You know, the spectrum of this is quite respectable overall. So something wrong here. That could still be an issue with those output transistors. Maybe we've not got the current gain that we should have there, even though the transistors check out. They're maybe not performing. So we'll go and look at that now, see if we can figure out the reason for this harmonic content.
So it seems like 2 steps backwards on this amplifier then. I took the module where we saw the distortion going high, and I measured the gain on the transistors, measured the HFE, and on surface level they look sort of semi-reasonable, but when I compare with the datasheet, what I find is that the HFE is actually significantly higher than the datasheet says the maximum number should be. So that's a wee bit questionable. And what I did then is I swapped the board, swapped the board over with the 2 different modules, and the distortion followed these transistors. And we do know these have been replaced before. We don't know the origin of them, so that raises further questions. And when we look at the marking on the different transistors, these are the good guys here, and we've got some kind of symbol of the manufacturer there. I don't recognise that. And these are obviously different. So, you know, given that the gain is reading higher than the data sheet suggests, and we've got this funny effect, I really wonder what's inside these guys. You know, are they really the BD50, BDY56, or, you know, is this some counterfeit thing going on here? We don't know. We'll never know. It could be they're just damaged in some way, and that's caused this funny business. But it seems kind of strange that the gain would then read high. So we're just generally suspicious of these parts. I've tried to source, you know, replacements again, but very hard to come by. These are long since obsolete. What is available is very expensive, and again, we just don't know what the origin is going to be. We don't know what result we're going to get. So what I'm going to do is we'll try some of these guys. This is On Semi, which used to be Motorola, and these are very good audio transistors, MJ15003. These are very expensive as well. These are like £10 each. So, you know, when you're looking at an old amplifier like this, and you're you know, before you do anything, this is your kind of parts cost, and we don't know what else we're going to find. But there we go. So we'll try a couple of these in this module and see what the distortion looks like on that. Right, so here's our new transistors installed then, and the other thing I did is the wiring between the transistors and the board, kind of feeble beforehand, and of course this is what's driving your loudspeaker. So I've changed that. I've put in some heavy, this is just some like mains cable here, chopped up. Put that in place, so that should improve that area there. So I think we're ready now. We'll connect it back up again and see how the distortion looks on this, and go from there.
So I've got the module connected back into the amplifier now, and you know, I've set the bias again, and here we are outputting 10 watts. And you know, before we changed these transistors, we were struggling to get any more than a watt before we got some serious distortion on the output. But this is as clean as can be, 10 watts out here. And if we go and actually look at the distortion numbers, here we are here, 0.003 something, and that's, you know, that's actually a little bit better than our simulation. Our simulation was about 0.004, so pretty good place we're in now. And my only observation here is that the noise floor kind of rises down at these the lower end of the band here, and that's going to be contributing to this distortion figure as well. and I think that's probably just related to that input op-amp. I'll maybe go and have a look at the datasheet for that and see if there's any clues there, but that's probably what's doing that, and both modules are the same, so quite normal. So all good. I'm going to go and change the transistors in the other module now, so that everything's matched. You know, we've got a matched pair, and then we'll install them into the amplifier. I think we're getting there now then. This is both modules in the unit powered up, and I've got a test signal on the input, and both outputs are connected to the scope. And I just wanted to, at this stage, before I really install these modules properly, I want to check all the knobs and buttons that they're functioning properly and they're not noisy, etc. So here we are. If we turn up the volume, and I'm on 10 volts of division here, so 40 volts on the peak there, and I'm clipping just off screen. If I adjust my green trace up a bit, you can see there we're just clipping a flat line on the bottom there, so it's just clipping off screen there. So that's all good, and you can see actually that you can see the poor tracking on the volume control. I mean, this is a classic problem with kind of old school or cheaper volume controls. They're made up in different segments, and if you see now, both traces overlap. As I turn the volume down, the yellow trace is dominating, and then kind of lines up again, and then the green trace starts to dominate. And that's just a classic, just the sort of errors and specs in that volume control. And so you really have to use your balance, you know, to center your image with these kind of old school amplifiers. But anyway, all these knobs and buttons are working fine. There's our balance control working just fine there. So that's all good. Next thing then, I think I want to connect some loudspeakers, and I'm interested to see how hissy this amplifier is, given that noisy op-amp that we see on the power section there. So we'll try that, and then all being well there, I think we're ready to wrap up and play some music. Here's our Rogers A100 all complete then, and if we power up, there's just a wee delay before the relay kicks, and then our loudspeakers are connected. And there's definitely a bit of hiss coming through there, as we expected when we looked at the circuitry. Also, when you turn up the volume, there's a bit of 50 Hz comes through. So definitely room for improvement here. You know, we could look at changing those op-amps for something more modern, but that's probably a project for another day. I've still to, I need to source a new knob for the speaker port there, and also the auxiliary push button here. But we're all working, so let's just play some music and see how we go.